Hello and welcome. In this video, we want to take a look at the fundamental theorem of line integrals. Um, just the name itself might indicate that this is reasonably important. Um, Although I like to ask students, do you know any other fundamental theorems? And the answer is you might know two of them at this point. You might know some more, but there's the fundamental theorem of calculus, which you learn in Calc 2, and we'll go over that here in a moment. There's also the fundamental theorem of algebra that sometimes people know. Fundamental theorem of algebra essentially says an nth degree polynomial can be factored into n linear factors if you allow for complex coefficients. Anyway, fundamental theorem of line integrals is what we want to look at today. And it goes like this. Suppose that capital F is a vector field, which is actually the gradient of little f, where little f is a scalar function of several variables. And you've got a curve C that's defined in the domain of the vector field f, starting at r of a and ending at r of b, where r is the parameterization, right? R of t is the parameterization for C. Now, I'm being very vague here in the sense that I didn't say how many variables either the vector field capital F takes or the scalar function little f takes. I just said it's a function of several variables. If it was two variables, if f is, little f is a function of two variables, then capital F is going to be a vector field of two variables. And likewise, if little f is three variables, then this would have three variables as well. Okay? Or four or five, however many you want. The theorem works with any number of variables. And what it says is that the line integral of this gradient, you either call it grad of little f, or you could just use the capital F there, dotted with dr. So the line integral of this gradient field along the curve is equal to the function value f of the endpoint minus f of the start point, right? This started at r of a and ended at r of b. Does this look at all familiar? It should, because back in Calc 2 we had this thing called the fundamental theorem of calculus, part 2. Part 1 told us that every continuous function has an antiderivative and showed us what it was. But part 2 says if f is a continuous function on an interval from a to b, then the integral from a to b, the definite integral of f of x dx, is capital F of b minus capital F of a, where capital F of x is any antiderivative, right? Just find an antiderivative, plug in the endpoints, and subtract. Right? Sometimes we wrote that this way, where the integral of the derivative of capital F was just capital F evaluated at b minus capital F evaluated at a. And that's essentially, this is like a multivariable version of that fundamental theorem of calculus. That is, the gradient of little f is sort of like the derivative of little f, but a multivariable derivative because it takes into account the partial with respect to each one of the variables, right? And so if you're integrating this gradient along a curve, all you've got to do is figure out what the endpoints are, plug those into the function that you got the gradient from, and subtract, and that's the value. Now, the proof of this is beyond the scope of this course, but we will use the results nonetheless. You got to take you got to take a, what do I want to call it, an advanced calculus class probably to work through the proof of this theorem. But nonetheless, it's remarkably useful. Okay. So one thing to be aware of here is that the fundamental theorem of calculus, this one down here, right? Part 1 said that every continuous function has an antiderivative. So you can always, if this little f here is continuous, then you can find an antiderivative, you can plug in the endpoints and subtract and evaluate that integral. The problem is not every vector field is conservative. Not every vector field is the gradient of something else. If you're lucky and you have a vector field that is the gradient of something else, then the fundamental theorem of line integrals will say, hey, we can evaluate this by just finding the potential function and evaluating at the endpoints and subtracting. Okay. Essentially, little f here is the potential function for capital F. Capital F is the vector field. Little f is the scalar function whose gradient is that vector field. So it's the potential function. Let's do an example. So here's my scalar function, x squared minus y squared, and I will take the gradient, calling capital F the gradient of little f, and the gradient of little f is first take the partial with respect to x, which is 2x, and then take the partial with respect to y, which is negative 2y, and so those are the two components of my gradient field. And I'm going to just pick a random curve here. It's going, the curve is t squared comma t cubed, and I'm going to let t run from -1 to 2. I'm going to note that r of -1 is, plug a -1 in for t here and here, and I get 1 and -1. And if I plug a 2 in, then that will be 2 squared and 2 cubed for 4 and 8 for that one. So this curve is starting at the point 1, -1, and it's ending at the point 4, 8. Right. Now I want to integrate, I want to do the line integral of that vector field f along the curve C. Okay. Well, that vector field f is the gradient of little f, and the fundamental theorem of line integrals says, oh, let me just take the potential function, plug in the end point, r of 2, and subtract what I get when I plug in the start point, r of -1. Well, r of 2 was 4, 8, and r of -1 was 1 -1. Plugging those into the function, f of 4, 8, looking up here, 4 squared minus 8 squared, so that's 16 minus 64, and then plug in the 1 -1, so 1 squared minus -1 squared, so that's again 1 -1, and so I've got 16 minus 64 is -48, and 1 -1 is 0, so I get a grand total of -48. So I just did that line integral by finding the potential function, I started with the potential function, I didn't really find it, plugging in the endpoints and subtracting. Now, if I didn't know the fundamental theorem of line integrals, I would have to do it the old-fashioned way. The old-fashioned way, we would need to first of all calculate r prime. So remember, r was t squared, t cubed, so r prime is 2t comma 3t squared. Then the vector field integral along the curve here, I'm going to do it as a p dx plus q dy. My vector field, capital F, is p comma q, where p was 2x and q was -2y. And then so dx is the 2t from there, and the dy is the 3t squared from there. dt, substituting in the x from the parametrized curve, so x was t squared, and the y here is t cubed, and now everything's in terms of t, so I'll write that as the integral from 1 to 2 of all this stuff dt. Simplifying some things here, this is 4t cubed minus 6t to the 5th, and that's easy enough to find an antiderivative. It's t to the 4th minus t to the 6th. Integrate, evaluate between -1 and 2. So plug in the 2 in there, I get 16 minus 64, and then plug in the -1 in there, I get 1 -1. Subtracting, I get again -48. So what would you rather do, this or that? I would rather do that, the first thing we did. Now, except that, in general, and here's my caution, right? This only works if the vector field that you're trying to do a line integral of is conservative. And more so, you've got to find the potential function. I started this example with, here's a potential function, let's take its gradient and then do the line integral of that and see what happens, right? See that I can do this 2 different ways to get the same result. But in general, you don't know the potential function. You have to find the potential function. Okay, so we've got 2 things we still need to do, and we will do them in subsequent videos. We need to, first of all, establish when something is conservative and therefore has a potential function, and then how do you find the potential function? Okay. Those videos are coming up. Enjoy.